Okay, so here we're gonna just take a look at some properties of trees, and then go over two specific type of trees, or one more of a concept of properties of connected graphs, or just a general connected graph, and how are they related to trees, and then we'll get into our rooted trees here. All right, so just a couple of propositions here. We'll state these without proof, but more just we'll just take them to be true. All right. So these propositions come from our textbook, right? And we just kind of develop more of these properties for trees. We say that a graph T is a tree if and only if, right? So strong connection here. If and only if between every pair of distinct vertices of T, there is a unique path. Okay. All right. So we know that now this is another one of these proper way that we can define a tree, right? If and only if, right? Assign these properties, and then here a corollary of this kind of stems from the proposition is that a graph E is a forest if and only if between any pair of vertices in F. A graph E is a forest and a vertices in E. There is at most one path. All right, and here obvious from the previous one, if we have a tree, I know it's connected, so every pair there is a unique path, right? The correlate is just really, well, a forest is uh, not necessarily guaranteed to be connected, right? But the parts that are connected are trees, so it makes sense that while this follows almost just by the nature of a forest and a tree. Okay, all right. And again here, thinking of our rooted trees, however they look, right, there exists that unique path, right? Just because of the nature, there's no simple circuits, right? We never wind up back where we are started here, and it all just kind of flows in one direction here. Now there is a relationship in a tree between the vertices and the edges, right? So here for all trees, the edges are always one less than the vertices. Okay, so E edges, V vertices. All right. Okay, and then here, just a couple things here. Just imagine here, you had a tree of just two vertices. We see there's one edge, right? And you see no matter where I add another vertex, see here, all right, well, I just added an edge. All right, so three vertices, two edges, and again, it is connected, but there's no cycles, no, so this must be the way that we generated here. Let's say I add two more vertices. Right, sure I had two edges, but I'm always still, it's always one less than the number of vertices. Okay, now this isn't a formal proof. The book has a proof here, but this is asking to be proven using induction, which we haven't covered yet. We will cover it later. So things like this where we can kind of build this argument. Now, this is not a proof, right? This is more just kind of an example here, right? We want to generalize our proof, right? But the best way to do that is via induction, which we haven't covered here yet. So we'll hold off on doing that here. All right, now, the next concept here is this idea of a spanning tree. Now, this is a statement about connected graphs. So the definition of a spanning tree, right? It says given a connected graph, G, a spanning tree of G is a subgraph of G, which is a tree and includes all vertices of G. Right, and as it turns out, right, a theorem, which again we'll just hold to be true, we'll state without proof, every connected graph has a spanning tree. Okay, so again, this definition is for any connected graph. It doesn't have to be a tree, right? It states that there is an associated spanning tree of G that is a subgraph of G, which we covered in a previous video, which is a tree and includes all vertices of G, all right? So that's also, careful with that and, right? Not just any tree. The spanning tree must include all vertices of G. And as it turns out, every connected graph has a spanning tree, right? So let's take a look, for example, here at this particular connected graph. Okay, so let's say we had okay, so as we see here, we have a connected graph, clearly not a tree, right? We can see here, right, again, has a cycle, right? If it is a cycle, that is enough to just tell me that this is not a tree. But we can have a subgraph where we define it, let's say like this. All right, and now this is a spanning tree. And again, notice it includes all the vertices, and it is a tree. All right, and a subgraph, right? Now, it's not the only one, right? And again, here, also here, a subgraph contains all the vertices and is a tree, right? Tree contains no cycles. All right, so just kind of an interesting property to relate any connected graph to a tree. Now the last type of graph here is again when we think of trees, right, we think of the rooted trees, right? Where there's some kind of like hierarchy involved, or everything kind of stems from this original or first vertex, which we call the root. Right? So here we have a root, right? And we have all these different vertices associated with the root, right? So again, we use the very familial language here where we could say, all right, if this is the root, right, anything below that, the root, we can call this the parent, right? And anything below that is a child, right? And anything below that, or we can call the next level, kind of like grandparent or grandchild, excuse me, grandchild. Right, now if we get further, just to kind of simplify the language, right, if we're down here, right, as a way to just kind of establish a relationship with the root, we just say it's a descendant. And a descendant just means that there is a path to the root. Okay, and we could also here, at any level here of our rooted tree, we can establish, even if we just look at this kind of level here, we can define this to be our parent, and then the ones below it to be the children. All right, we always associate the parent as the one being closer to the root. Okay, so that's here the idea of a rooted